We experience gravity every day, pull it down to Earth with every step we take. It's easy to forget that this same force governs the motions of planets, stars, and galaxies too. And just as the gravitational pull between a woman and the Earth keeps her anchored to the ground, so does the gravitational tug between objects in space keep them locked in an intricate, three-dimensional ballet. Over eons, these gravitational interactions have orchestrated the birth of planets, reshaped entire galaxies, and driven some stars to cannibalize their neighbors. Gravity has also steered our solar system on a once-a-year collision course with a cloud of dust and gas called the Orion Nebula in about 100 million years. This cloud will become the next chapter in the history of our solar system and the story of our planet. But first, let's examine smaller-scale collisions. A rocky world with a mass about half that of Earth travels through space. Its name is not known because it has not yet been discovered. Its lonely journey is about to come to an end. A few million miles away, a larger rocky world twice as massive as Earth lies in wait. Eventually, the two objects pass close enough for their mutual gravity to yank them toward each other. The sky around them fills with fire as their atmospheres burn away. Then they collide, combining into a single object roughly the size of our moon. Scientists think these collisions were common in the early solar system and may have played a role in building the planets themselves. In fact, some astronomers believe that our moon formed when a Mars-sized object crashed into Earth. Now imagine a much larger collision. Two galaxies are racing toward each other, locked in a death embrace. As they approach, the gravitational forces between them increase dramatically. The bright blue star in the upper left corner of the screen is actually the core of a globular cluster, a dense group of stars within a galaxy. It's traveling so fast that its escape velocity exceeds the speed of light. That means nothing, not even light, can escape its gravitational pull. It will literally disappear beyond the horizon. Meanwhile, a red giant star is being flung out of the frame by the gravitational pull of a supermassive black hole. These extreme events are happening on both sides of the collision, and the galaxies continue crashing into one another. Finally, the two spiral galaxies merge into a single elliptical galaxy. While these cosmic collisions can be immensely destructive, they can also be immensely creative. The debris thrown out of a galaxy during a collision can form new stars, planets, and even whole new galaxies. In this image, a pair of merging galaxies is surrounded by glowing blue clouds of gas and dust, the building blocks of new stellar systems. Now, let's return to the peaceful-looking night sky and consider what we know about its past. Our galaxy, the Milky Way, has been flying through space for billions of years, pulled along by a combination of inertia and gravity. Now, like all galaxies, the Milky Way is moving through a vast sea of space, a ceaseless flow of matter and energy that permeates the cosmos. But it's not empty. Hidden within this sea are countless objects, some of them quite large, that the Milky Way cannot avoid. And over time, these near-miss encounters have profoundly affected the galaxy we call home. The Milky Way has already collided with several small galaxies, including the Sagittarius dwarf and the Canis Major dwarf. These encounters were not gentle. They stripped billions of stars from the dwarfs and scattered them throughout our galaxy. But the Milky Way has also suffered more catastrophic collisions in the past. About 10 billion years ago, it merged with another large spiral galaxy. Today, the remnants of that galaxy form a thin, flat disk in the center of the Milky Way, home to many of our closest neighbors, including the bright blue globular cluster at the top of your screen. As we look to the future, we can see that the Milky Way is hurtling toward another collision. In about 5 billion years, our galaxy will slam into the Andromeda galaxy, a huge spiral galaxy similar to the Milky Way. This encounter will change both of them forever. Like two dancers held in an embrace, the galaxies will swirl around each other. Stars will be flung from their familiar paths and crash into new ones. Some will wander into strange new neighborhoods. Others will find themselves hurled into the cores of their galaxies. Entire star clusters could be ripped from the galaxies, leaving behind only a faint echo of light. Most of the stars won't stray too far from their original paths, however, and after the collision, the Milky Way will look much like it does today. That is, if it even exists anymore. In fact, the two galaxies will merge to form a single galaxy, much like the two spiral galaxies did billions of years ago. Our place in the universe will be forever altered. Even now, the collision is reshaping us, pulling cosmic objects into the paths of one another and forging new worlds from the wreckage of old. The universe may seem still and silent, but it is anything but. Collisions are the architect of the universe. They have shaped our solar system, our galaxy, and the world we call home. From the smallest asteroid impact to the grand collision between the Milky Way and Andromeda. These violent encounters drive the engine of creation and destruction. As we look up at the stars, let us remember that the universe never ceases to amaze. It is a place of both beauty and terror, where worlds are born from chaos and galaxies dance together in an eternal ballet. For in the grand scheme of things, we are all just passengers on a rock hurtling through space, forever at the mercy of the laws of gravity and the will of the collision. At the heart of every collision in the universe lies a single, unrelenting force: gravity. Gravity is the weakest of the four fundamental forces of nature, but because it always attracts and never cancels out, it dominates the universe at large scales. It is gravity that binds planets to stars, stars to galaxies, and galaxies into clusters and superclusters. And it is gravity that inevitably pulls these objects into one another's paths. The universe has been expanding and cooling for 13.8 billion years. During that time, gravity has steadily pulled matter together, building up great structures of stars and galaxies. But from the very beginning, gravity has also pulled these structures apart. So from the largest to the smallest scale, collisions are all around us. They are written into the very fabric of the cosmos. Our story begins with the Big Bang. Our best theory for the origin of the universe posits that everything started small, hot and dense. Then the universe expanded and cooled, allowing matter to clump together and eventually form the first stars, galaxies, and clusters. But the same gravitational force that built structure also guaranteed instability. Massive objects warp space-time, curving the paths of others nearby. If two galaxies form close enough, their mutual pull will bring them together. If two stars orbit in a binary pair, tidal forces may strip one apart. Collisions, then, are not rare accidents. They are natural consequences of gravity's long reach. In the solar systems that surround other stars, collisions play a similar role. In fact, they may be even more important. Most solar systems form from giant clouds of gas and dust. As the cloud collapses, a baby star takes shape at its core. Meanwhile, bits of rock and dust swirl around the star in a disk. Eventually, electrostatic forces cause dust grains to stick together, forming kilometer-sized bodies called planetesimals. These fragments grow as they sweep up more dust, but some get flung away, never to return. Collisions between planetesimals range from gentle to catastrophic. Sometimes a small fragment simply bounces off a larger one, gradually finding a stable orbit. Other times, a collision strips fragments from a protoplanet's surface, creating the building blocks for moons. Still others send an object hurtling into the star or out into deep space. These impacts determine which planets survive, which worlds are destroyed, and what moons are born. Our own Earth is a direct product of this violent process. It formed early in the solar system has history, when a Mars-sized body named Theia crashed into a proto-Earth. This cataclysmic collision ejected massive amounts of material into orbit. Over time, some of that debris coalesced to form our moon. So while the solar system we know today seems stable, it too is a product of countless collisions. But collisions don't just shape solar systems, stars collide too. In the most crowded stellar nurseries, it can get downright dangerous. When a star ventures too close to its neighbor, gravity can have many effects. It can rip apart circumstellar disks, fling planets into interstellar space, or even cause two stars to merge. In a close encounter, the gravitational tug can be strong enough to pull material from one star's atmosphere to the other. Tidal forces stretch and distort both stars, which heats their surfaces and triggers a burst of energy. This energy can blast material into space, or even power a new star's formation. Merging stars, meanwhile, can release huge amounts of energy in the form of light and radiation. Some merged stars explode as supernova, leaving behind neutron stars or black holes. Others become even larger, hotter and more unstable than before. So, the life cycle of a star is punctuated by collisions that can alter its path and even change its nature. On the grandest scales, entire galaxies collide, like planetary or stellar crashes. Galactic collisions are rare events, but they happen. Unlike those smaller crashes, however, galactic collisions are drawn out over billions of years. Each galaxy contains hundreds of billions of stars, yet most of a galaxy is empty space. When two spiral galaxies merge, for example, most stars will pass each other harmlessly. A few close encounters can trigger bursts of star formation, but the real action is in the centers of the galaxies. Their supermassive black holes spiraled toward one another, passing close enough to exchange material. As they approach their ultimate merger, these black holes accelerate, unleashing powerful jets of radiation and gravitational waves. It is here, at the galactic scale, that cosmic collisions reveal their full creative power. Many of the most beautiful galaxies we see today, distorted spiral arms, rings and starburst regions, are scars of past collisions. From the smallest asteroid strike to the merging of supermassive black holes, collisions follow one rule: the universe is shaped by interactions, not isolation. Every star, every planet, every galaxy exists not in solitude, but in a constant gravitational dance with its neighbors. These dances sometimes end in balance, like planets in stable orbits, but often they end in catastrophe, collisions that destroy and transform. This is the foundation of our story. Collisions are not random accidents. They are built into the very laws of nature. Without them, the universe would be a quiet, featureless void. With them, it becomes a place of constant renewal. When you think of the universe, you may picture a static place, an unchanging sky full of familiar constellations. But in reality, space is a realm of motion and change. Planets orbit stars, stars race through galaxies, and galaxies collide in an endless cycle of birth, death, and rebirth. Our tendency to view the universe as unchanging reflects our human limitations. We can only directly observe a tiny slice of space and time. But beyond our immediate view, the cosmos is a dynamic stage where objects of unimaginable scale and power play out their existence through collisions. But why do these collisions occur? Why is the universe such a violent place? To understand the driving force behind these collisions, let's look at Newton's first law of motion, which states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. This means that all objects in the universe are inherently stable and resist changes to their state, whether it's a planet, a comet, a star, or a galaxy. However, forces do exist in the universe that can overcome this inertia, bringing objects together. Gravity is perhaps the most influential force on large scales. As objects pass each other in space, their mutual gravitational attraction causes them to slow down and curve toward one another. This effect is more significant for objects with greater mass, because their gravitational pull is stronger. So it seems that much of the action in the universe comes down to gravity. And what better way to explore this phenomenon than by diving into some of the most iconic collisions the universe has to offer? So sit back, relax, and get ready to be amazed as we take a closer look at the incredible collisions happening in our universe. If the first part of our journey laid the groundwork for why collisions are inevitable, this chapter takes us to the front row of some of the most extraordinary examples. These are not abstract theories, but real iconic collisions that astronomers can observe, predict, and in some cases, watch as they unfold across millions of years. The Milky Way Andromeda collision, a date with destiny, our own galaxy, the Milky Way, is on a collision course with its nearest large neighbor, the Andromeda galaxy, M31. Andromeda is about 2.5 million light-years away, a staggering distance by human standards, but in cosmic terms, that's uncomfortably close. The two galaxies are rushing toward each other at roughly 110 kilometers per second. In about 4 to 5 billion years, they will collide. But what does a galactic collision actually look like? Surprisingly, it is not the apocalyptic smash we might imagine. Galaxies are mostly empty space. If you scaled the sun down to the size of a marble, the nearest star would be several thousand kilometers away. This means that in the Milky Way Andromeda collision, almost no stars will collide directly. Instead, gravity will twist both galaxies into elongated shapes, pulling vast arcs of stars and gas into intergalactic space. Over billions of years, the two will merge into a new, larger, elliptical galaxy, sometimes nicknamed Milkomata. For Earth, the future is uncertain. Our solar system could be thrown into a new orbit around the galactic core, flung into interstellar space, or remain relatively undisturbed. From the surface, if humanity or its descendants are still here, the night sky would be transformed into a swirling, luminous dance of stars. Galactic mergers across the universe. While our collision with Andromeda is a prediction, galactic mergers are already observable across the universe. With telescopes, astronomers have captured spectacular snapshots of galaxies in the act of colliding. The antenna galaxies NGC 4038, 4039. These two galaxies, 60 million light-years away, are locked in a violent embrace. Their spiral arms have been torn apart and stretched into long antenna-like tails. Within these tails, gas clouds collapse to form thousands of new star clusters. NGC 6240, a chaotic galaxy with two supermassive black holes spiraling toward one another at its center. When they merge, they will unleash colossal gravitational waves that ripple through space-time. ESO 137001, a galaxy plunging through a cluster, leaving behind a dramatic trail of stripped gas that glows in X-rays, a reminder that even intergalactic space is not empty, but filled with plasma and dark matter that shape galactic fates. Each of these collisions shows a different phase of the process: initial contact, tidal disruption, central black hole mergers, and eventual stabilization. Over time, they transform graceful spiral galaxies into featureless ellipticals, reducing star formation but leaving behind colossal structures. Colliding neutron stars? Cosmic catastrophes? If galactic collisions are majestic, neutron star collisions are catastrophic. Neutron stars are the dense remnants of massive stars that have gone supernova. A single teaspoon of neutron star matter weighs billions of tons. When two neutron stars orbit each other in a binary pair, they slowly spiral inward as they lose energy through gravitational waves. Eventually, they collide. The result is one of the most violent events in the universe. When neutron stars merge, they unleash gamma bursts, beams of high-energy radiation so powerful they can outshine an entire galaxy for seconds. They forge heavy elements like gold, platinum, and uranium, scattering them across space. The gold in your jewelry was once born in such a collision. They create massive ripples in spacetime, detectable by instruments like LIGO and Virgo. The first confirmed detection came in 2017, when gravitational wave observatories and telescopes around the world observed GW 170817, a neutron star merger 130 million light-years away. For the first time, humanity witnessed light and gravitational waves from the same event, a milestone in modern astronomy. Cosmic lessons from collisions. Each of these iconic collisions teaches us something profound. From Andromeda, we learn about our own future and the long-term evolution of galaxies. From galactic mergers, we understand how structure grows and transforms across the universe. From neutron star collisions, we uncover the origins of the heaviest elements and confirm predictions of Einstein's relativity. These events are not just spectacular, they are essential. Without collisions, the universe would lack the raw materials for planets, the conditions for starbursts, and the cosmic drama that shapes everything we know. It's important to note that while these collisions are incredibly destructive, they also create the conditions for new life to begin. The heavy elements forged in the cores of dying stars become the building blocks of new worlds. The gas and dust expelled by colliding galaxies forms the raw material for future star formation. Even the energy released in these collisions can trigger the birth of new stars. So while collisions may seem like violent, destructive events, they are also a necessary and positive force for the universe. The study of collisions helps us understand not only how the universe began, but also how it will end. By observing distant galaxies colliding, we can see what the fate of our own Milky Way has in store for it. And by analyzing the debris left behind by neutron star collisions, we can uncover the origins of some of the most precious elements on Earth. As we continue to explore the vastness of space, we will undoubtedly discover many more iconic collisions that shape our universe. With each discovery, we gain a deeper understanding of the fundamental forces that govern the cosmos. And who knows what other wonders we might find as we delve deeper into the mysteries of the universe. For billions of years, our universe has been a bustling place. Stars have exploded, galaxies have collided, and black holes have grown. Amidst this cosmic chaos, one question keeps astronomers up at night. What really happens when galaxies collide? You might think it's all fiery destruction, but you'd only be seeing the tip of the iceberg. Behind the sparkling show is a drama of unseen forces reshaping galaxies, driving explosive events, and maybe even seeding the universe's first supermassive black holes. It's me, and you're watching this channel. Join me today as we delve into the heart of the collision zone, where the most dramatic events in the universe unfold. Some say that behind every great tragedy lies an even greater opportunity for rebirth. And nowhere is this more evident than in the world of astronomy. For what appears to the casual observer as mere collisions of stars and planets are actually catalysts for some of the most awe-inspiring spectacles in the cosmos. One such spectacle is the birth of new stars. When two celestial bodies collide, it's not uncommon for the resulting explosion to trigger the collapse of nearby gas clouds. These clouds, normally stable and serene, become violently disturbed by the shock waves of the collision. As the gas condenses in response to this sudden disturbance, gravity takes over and pulls in more material, giving rise to glowing balls of hot plasma. These protostars, born from the ashes of the old, carry within them the potential for renewed life. But this cycle of death and rebirth doesn't end with the stars. Entire galaxies, too, find themselves transformed by these cataclysmic encounters. As galaxies collide, their stars hurtle into each other, reshaping the very structure of the galaxies. But in this grand upheaval, new structures emerge, grand arcs and rings of stars that were once jumbled and chaotic. It's as if the universe itself is engaged in a cosmic dance, using collisions as steps to create breathtaking new patterns. But what if I told you that these collisions don't just shape the structure of galaxies? They may have played a pivotal role in seeding the universe with the very building blocks of life. Yes, you heard me right. Some scientists believe that these collisions may have delivered the crucial ingredients for life as we know it. Picture this, a dense gas cloud in the early universe, a birthplace for the universe's first stars. These stars, short-lived and massive, burn brightly before exploding in supernova, scattering elements like carbon and oxygen into the void. This material, enriched by the stellar explosions, becomes the very fabric of future planets and perhaps even life itself. In essence, collisions in the early universe may have served as cosmic mixing vessels, dispersing the ingredients for life far and wide. However, the universe doesn't limit itself to such simple tales. There's always a twist, a curveball, that keeps things interesting. And in the case of galactic collisions, the twist comes in the form of a time frame. For these collisions aren't instantaneous events. They play out over billions of years. During this extended period, the participating galaxies continue to evolve, experiencing internal changes that reflect the external forces acting upon them. Stars continue to form and fly. Black holes grow, and gravitational interactions continue to reshape the galaxies involved. In essence, a collision isn't just a moment in time, but a process that spans eons, gradually reshaping the participants in ways both subtle and profound. You might wonder, why do galaxies, mostly composed of empty space, collide so dramatically? The answer lies in their invisible components, the dark matter halos. These massive, invisible regions surround galaxies, extending far beyond the visible stars and dust. When galaxies collide, it's these dark matter halos that often make the first contact, setting in motion a chain of events that culminate in the spectacular displays of light and energy we observe. Moreover, dark matter plays a crucial role in determining the outcome of a collision. The distribution and behavior of dark matter can significantly influence how galaxies merge, whether they are flung apart or drawn together, and ultimately how they evolve as a result. It's as if the universe itself is guided by an invisible hand, orchestrating these collisions to create a grand design that we are only beginning to understand. Now let us turn our attention to an event so awe-inspiring that it's earned the title of the most energetic explosion in the universe, the Gamma ray burst. Imagine a flash of light so bright it outshines the combined brilliance of every star in the night sky. That's the power of a gamma-ray burst, an astronomical phenomenon that briefly dominates the universe with its sheer intensity. And guess what? These cosmic fireworks are not just random occurrences. They have a fascinating connection to collisions. Some gamma-ray bursts are thought to occur when two neutron stars, or a neutron star and a black hole, collide in a grand cosmic tango. The immense energy released in this collision is then expelled in a fiery burst of gamma rays, a spectacle so brilliant that it can outshine entire galaxies. But the connection between collisions and gamma-ray bursts goes even deeper. Recent studies suggest that collisions may play a vital role in the formation of long-duration gamma-ray bursts. This is a game-changing revelation that challenges the traditional view of these bursts as solely the result of individual star deaths. Instead, it highlights the interconnectedness of celestial events. A single star's demise may trigger a cascade of events, including collisions leading to the universe's most luminous explosions. It's as if the universe is engaged in a continuous cycle of birth, death, and rebirth, with collisions serving as the catalyst for these dramatic transformations. And yet the universe continues to surprise us. Recent research suggests that collisions may also be the key to understanding another baffling cosmic phenomenon: fast radio bursts. These are intense pulses of radio waves that originate from distant galaxies and last only a few milliseconds. While their exact cause remains a mystery, astronomers believe that collisions between galaxies, or between a galaxy and a black hole, could be the culprit behind these enigmatic bursts. Now, you might wonder, how do we know about these collisions if they happen so far away? Well, that's where the scientific community has turned to computer simulations. By simulating these collisions in laboratory conditions, researchers are able to observe the dynamics of these events up close. With advanced telescopes and simulation capabilities, we are now poised to witness these collisions in a way that was never before possible. We can observe the intricate details of the merging process, the interactions between dark matter halos, the birth of new stars, and even the occurrence of gamma-ray bursts. It's as if the universe is opening its most secretive chapters to us, revealing the intricate mechanics that drive its most spectacular events. The study of collisions is no longer confined to dusty books or theoretical models. It's alive, dynamic, and unfolding before our very eyes. However, amidst all these revelations, there's still much that remains shrouded in mystery. Take, for example, the growth of supermassive black holes. These colossal black holes, millions or even billions times the mass of our sun, reside at the hearts of most galaxies. But their origin story remains a cosmic enigma. Could collisions be the missing piece of this puzzle? Scientists believe that collisions between primordial galaxies may have provided the initial kick that these giants needed to grow. But the details of this process are still a cosmic secret waiting to be uncovered. In the grand theater of the cosmos, collisions take center stage, playing a pivotal role in shaping the universe as we know it. From triggering the birth of new stars and galaxies to influencing the behavior of supermassive black holes and driving gamma bursts, collisions are the universe's master sculptors. As we continue to explore the depths of space and unravel the complexities of the universe, we'll undoubtedly uncover more facets of this cosmic dance. Each discovery will bring us closer to understanding the delicate balance that has shaped the universe, reminding us that even in the vast expanse of space, nothing exists in isolation. Every event is connected, every action has a consequence, and every collision is a step towards a deeper understanding of the universe. What do you think? Do you find the idea that collisions play such a significant role in the universe fascinating or terrifying? Let me know your thoughts in the comments section below. Your feedback is my inspiration. Remember, with every collision, the universe finds a way to renew itself, to shape new structures and processes, so too in our lives. For billions of years, Earth has not been immune to the grand cosmic ballet of collisions. In fact, our very existence, the continents, the oceans, even life itself, may be the product of ancient crashes that forever altered the course of our planet's history. But what if I told you that these impacts didn't just shape Earth's past, they might also hold the key to its future? Welcome to my channel. And today, let us embark on a journey through time and space to explore how collisions have been Earth's constant companions throughout its existence, and why they might hold the secrets to our planet's destiny. The largest impact in Earth's history is so monumental that it not only changed our planet forever, but also left an indelible mark on the sky. The birth of the moon. The giant impact hypothesis proposes that around 4.5 billion years ago, long before the first humans or dinosaurs graced the Earth, our planet collided with another celestial body. This wasn't your average fender bender. It was a full-on crash between Earth and a Mars-sized protoplanet scientists call Theia. Imagine the force of two planets smashing into each other. The consequences would be catastrophic. But this cosmic collision didn't destroy Earth. Instead, it fundamentally reshaped it. As the two planets merged, their combined mass was flung into the surrounding space. This debris, composed of rock and dust, didn't just dissipate into the ether. It circled our nascent Earth, held captive by our planet's gravity. Over millions of years, this orbiting debris coalesced, clumped together under the force of gravity, eventually forming the moon we know today. It's like the Earth threw a cosmic tantrum and created its very own personal satellite to keep it company. But why do we think this happened? What evidence do we have to support this radical idea? First, the moon's composition closely resembles that of Earth's mantle, the layer of our planet beneath the crust. This similarity suggests that the moon didn't form independently but was instead ejected from Earth during their tumultuous encounter. Second, simulations of planetary formation indicate that giant impacts were commonplace in the early solar system. Back then, everything was a bit rowdy. Planets were migrating all over the place, crashing into one another and exchanging chunks of themselves. And third, the moon's surprisingly small iron core lends credence to this theory. If it had formed independently, we'd expect a more substantial core. But a core of this size is precisely what you'd anticipate from a body created out of Earth's mantle and crust. And while some argue that they could have been entirely consumed by Earth, leaving no trace, others propose that parts of it still linger within our planet. Computer simulations suggest that some fragments from the Theia may have sunk deep into Earth's mantle, forming dense pockets known as large low-velocity provinces. These areas are so vast that they could harbor entire moons within them. So not only does the moon hold clues about its own origins, but it also offers a glimpse into the potential remnants of its parent body. But the significance of this impact goes beyond just the moon. Our lunar companion plays a pivotal role in stabilizing Earth's axial tilt, keeping it at a consistent 23.5 degrees. This stability ensures that one hemisphere doesn't perpetually bask in sunlight, while the other remains in darkness. It also drives tides and mixes nutrients in the oceans, a process believed to be crucial for the origin of life. By slowing Earth's rotation over billions of years, the moon has lengthened days from 6 hours to our current 24-hour cycle. It's as if the moon, born from a cataclysmic event, has spent its existence gently guiding Earth and life itself towards stability and complexity. They may be gone, but its legacy lives on in the moon and in us. But the story doesn't end there. Billions of years after the Theia impact, Earth would experience another dramatic collision, one that would change life on our planet forever, the Chicxulub impact. Fast forward to about 66 million years ago, the late Cretaceous period was coming to an abrupt end. The reign of the dinosaurs was about to meet its demise near the Yucatan Peninsula in Mexico. As an asteroid or comet approximately 10 kilometers wide slammed into Earth. The impact unleashed an astonishing amount of energy equivalent to billions of nuclear bombs detonated all at once. The asteroid, now known as Chicxulub, triggered earthquakes, tsunamis, and a massive release of dust and gases into the atmosphere. The immediate aftermath was devastating. Plants were wiped out, many marine species perished. But the true extent of the disaster unfolded over the next few years. The debris from the impact rose into the atmosphere, blocking sunlight and plunging Earth into darkness. Temperatures plummeted, leading to an ice age. With the sun obscured, photosynthesis ground to a halt, and the food chain collapsed. Dinosaurs, already under pressure from previous environmental shifts, were unable to adapt to these drastic changes. Their reign of nearly 200 million years came to an end. But amidst this devastation, there was a glimmer of hope. Small mammals, ancestors of modern whales and bats, survived the apocalypse in the darkness. These survivors would eventually give rise to larger animals, including our primate relatives and ultimately humans. The impact that marked the end for the dinosaurs became the catalyst for our own evolution. It was as though the universe itself orchestrated a cosmic baton exchange, passing the torch from one dominant species to another. And while the end Cretaceous extinction event is perhaps the most well-known, it wasn't an isolated incident. Our planet's history is dotted with smaller but significant impacts. Between 4 and 5 billion years ago, Earth endured a relentless barrage of asteroids and comets known as the Late Heavy Bombardment. These collisions delivered water and organic molecules to our planet, potentially seeding the conditions for life. Smaller impacts continued throughout the millennia, leaving their scars on Earth's surface and in the layers of rocks. The Chicxulub impact left its mark in the Yucatan, and the Younger Dryas impact, about 12,900 years ago, carved channels in North America. These events are stark reminders that Earth has always existed in the shadow of cosmic uncertainty. As we gaze up at the night sky, it's easy to feel as if Earth is a solitary island, suspended in the vast expanse of space. Yet our planet's history tells a different story. It reveals a world forever shaped by cosmic collisions, both gentle nudges and cataclysmic crashes. From the birth of the moon to the extinction of the dinosaurs and the countless impacts that peppered our planet's history, collisions have been Earth's constant companions. Each impact has left an indelible mark, influencing our planet's tilt, its climate, its oceans, and even the course of life itself. We are the products of a planet that has danced with asteroids, grappled with comets, and embraced its volatile past. But as we contemplate the role of collisions in our planet's story, a new question arises. Could future collisions hold the key to Earth's destiny? Perhaps there's a role for impacts in shaping our planet's future, delivering essential resources or nudging life beyond Earth towards new frontiers. After all, the collisions that have shaped Earth's past have not only destroyed, but also created, paving the way for the complex world we know today. Theia's crash may have given birth to the moon, our stabilizing companion, and Chicxulub's impact, despite ending the dinosaur era, allowed mammals like our ancestors to flourish. It's as if Earth's story is written in collisions, narrative of destruction and creation, of challenges and opportunities. As we look ahead, we can't help but wonder how future impacts will shape our world. Will they bring new life or pose existential threats? Only time will tell. But one thing is certain, Earth's story is deeply intertwined with collisions, and our planet's future may well lie in the hands of cosmic chance. This is a unit on the human gaze. It's a part of a larger series called Seeing Beyond Sight, which asks what we actually see when we look up at the night sky. In this episode, we're going to talk about how we detect and understand collisions in space, how they shape the universe, and sometimes threaten our existence. For most of human history, the idea of worlds and stars colliding was unthinkable. The night sky appeared timeless and unchanging. Stars burned steadily, planets traced predictable paths, and Earth felt stable beneath our feet. It was until the rise of modern science that humanity began to uncover the violent reality hidden in the cosmos. Early clues. Craters and catastrophes on Earth. The first evidence of collisions came from right here at home. For centuries, large craters were thought to be volcanic. But in the 20th century, researchers like Eugene Shoemaker revealed their true nature impact scars left by asteroids and comets. Meteor Crater in Arizona, formed about 50,000 years ago by an iron meteorite, was one of the first confirmed extraterrestrial impact sites. This realization rewrote our understanding of Earth's history. The smooth blue marble we inhabit was not safe from cosmic events. It was shaped by them. A turn for the telescope. Merging galaxies and crashing comets as telescopes improved, astronomers began to witness collisions unfolding across the universe. In the 1990s, the Hubble Space Telescope captured breathtaking images of galaxies in the process of merging. Spiral arms stretched and twisted, stars flared into new bursts of formation, and black holes devoured gas at the hearts of colliding galaxies. One of the most striking observations came in 1994, when comet Shoemaker-Levy 9 slammed into Jupiter. Over several days, fragments of the comet crashed into the giant planet, leaving Earth-sized scars visible even through backyard telescopes. For the first time, humanity witnessed a large-scale impact in real time, proof that collisions weren't just ancient relics, but ongoing phenomena. Simulations. Collisions on supercomputers while telescopes gave us images, computer simulations gave us motion. By modeling the physics of gravity, gas dynamics, and dark matter, scientists could recreate galaxy mergers, star collisions, and planetary impacts. These simulations revealed that collisions can trigger starbursts, massive waves of new star formation. Planetary systems are sculpted by close encounters and impacts, explaining odd orbits and tilted worlds. Even black holes may merge, sending ripples of energy through space-time itself. The idea that the universe is not static, but dynamic and violent, became undeniable. When light meets gravity, the gravitational wave revolution. The greatest leap in our ability to see collisions came in 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history. It detected gravitational waves, tiny ripples in space-time, caused by the merger of two black holes over 1 billion light-years away. This was a new kind of astronomy. For the first time, we weren't just seeing light from collisions. We were feeling the distortions of space-time they created. 2 years later, in 2017, LIGO and its European counterpart, Virgo, detected the collision of two neutron stars. Unlike black holes, neutron stars produce both gravitational waves and light. Telescopes around the world caught the afterglow of the explosion, observing the birth of heavy elements like gold and platinum. This discovery connected multiple fields of science: astronomy, through the light we observed; physics, through the gravitational waves we measured; chemistry, by showing where many of the elements on Earth originated. It was a unifying moment, proving that cosmic collisions forged the very building blocks of our world. Missions that move. Hunting for worlds and asteroids today, space agencies actively watch for potential collisions. Potentially hazardous asteroids, or PHAs, are regularly scanned for signs of danger. In 2022, NASA's Double Asteroid Redirection Test, or DART, made history. It deliberately crashed a spacecraft into the asteroid Dimorphos, pushing it slightly off course. This was the first demonstration of planetary defense technology. Though the effect was small, it showed humanity has the capability to alter the trajectories of asteroids, potentially saving Earth from a future impact. Earth impact craters. Earth is covered with impact craters, some dating back billions of years. Many have been eroded beyond recognition, but some remain remarkably preserved, offering direct evidence of our planet's turbulent past. Here are a few notable examples. The Barringer Crater, formerly known as the Meteor Crater. Located in northern Arizona, this crater is one of the youngest impact sites on Earth. It's estimated to be around 50,000 years old. Its well-preserved rim and exposed breccia provide valuable insights into the mechanics of asteroid impacts. The Chesapeake Bay Crater. Buried beneath the waters of the Chesapeake Bay in Virginia, this impact structure is estimated to be around 35 million years old. Evidence of the impact, including shocked quartz and tektite-strewn fields, extends far beyond the present-day limits of the bay, indicating a much larger original crater. The Chicxulub Crater. Located on the Yucatan Peninsula in Mexico, this crater is famous for marking the site of the asteroid impact that led to the extinction of the dinosaurs around 66 million years ago. Key evidence includes a layer of iridium-rich sediment found around the world, shocked quartz tektites, and an oil exploration well that accidentally tapped into the crater's underground lake. Other notable craters include the Vredefort Crater in South Africa, believed to be the largest verified impact structure on Earth, and the Sudbury Basin in Canada, which hosts the world's largest nickel and copper reserves, a testament to the economic significance of impact-related mineral deposits. Seeing the unseen, indirect evidence of impacts. While direct observations of impact structures are invaluable, indirect evidence also provides crucial insights into Earth's bombardment history. Here are a few examples. Shocked quartz. When rocks are subjected to extreme pressures and temperatures associated with high-speed impacts, they undergo physical and chemical changes. One of the most reliable indicators of impact is the presence of shocked quartz. This form of quartz has unique microscopic features, including planar deformation features, or PDFs, which are tiny flat surfaces within the crystal structure. PDFs are created when the quartz is rapidly compressed and then released, a process that only occurs during violent impacts. Tektites during an impact event. The intense heat generated can melt rock and soil, which is then ejected into the atmosphere. As these materials rise rapidly, they can form into glassy objects known as tektites. Tektites are typically dark in color due to the high temperatures they experience, and they often have unusual shapes and sizes. The presence of tektites strewn across a geographic area can indicate the location of a nearby impact crater. Shatter cones. Shatter cones are unique geological features that resemble ice cream cones and are created by the intense shock waves of an impact. They are typically found protruding from bedrock in areas that have experienced large-scale impacts. These cones are formed as fractures radiate outward from the impact point, compressing and deforming the surrounding rocks. Microtektites and micrometeorites. Microtektites are tiny glassy fragments produced in the same manner as tektites, but they are much smaller, often no bigger than a grain of sand. Similarly, micrometeorites are small pieces of meteorites that have survived the journey through the atmosphere. It's landed on Earth. Both microtektites and micrometeorites can be analyzed to determine their origin and provide clues about past impact events. Cosmological evidence for collisions. Our understanding of collisions goes beyond what we can directly observe. By studying the chemical signatures of stars and comparing them to laboratory recreations of cosmic events, astronomers piece together clues about stellar collisions. One example is the abundance of carbon in space. Stellar collisions are thought to play a significant role in producing this element, which is vital for life as we know it. Laboratory experiments that simulate conditions similar to those found in colliding stars show how carbon can be synthesized in such environments. By analyzing the spectra of stars and searching for specific spectral lines, astronomers can identify the presence of carbon and other elements produced in collisions, providing further evidence for the importance of these events in shaping the chemical composition of the universe. Another line of evidence comes from studying binary star systems. Many stars exist in close proximity to one another, and observing these systems provides insights into the dynamics of stellar collisions. By measuring the properties of binary stars and simulating their behavior, astronomers can gain a better understanding of the frequency and outcomes of collisions in such systems, helping to build a more complete picture of their prevalence and impact throughout the universe. Planetary defense. From observation to intervention, as our ability to detect and understand collisions improves, so does our capacity to intervene. The DART mission marks a significant step in this direction. By successfully demonstrating the feasibility of asteroid deflection, DART paves the way for future missions aimed at preventing potential threats to Earth. Continued efforts in planetary defense, coupled with enhanced observation and early detection capabilities, will ensure that humanity is better prepared to safeguard its existence against collisions from space. The future of collision science, as our technological capabilities continue to advance, the future of collision science holds exciting possibilities. Improvements in telescope technology will allow us to observe collisions in greater detail and at greater distances. Advanced computer simulations will provide more accurate and comprehensive models of these events, enabling us to better understand their complex dynamics. Moreover, the development of new space-based missions dedicated to observing and studying collisions will expand our knowledge of these phenomena. By combining observations, simulations, and theoretical work, the scientific community will continue to unravel the mysteries of collisions, shedding light on their frequency, intensity, and effects on celestial bodies and the universe as a whole. In conclusion, the study of collisions has come a long way from its early days of telescopic observations and computer simulations. With the advent of gravitational wave astronomy and planetary defense missions, our understanding of collisions has deepened, and our ability to interact with them has grown. As we continue to explore the vast expanse of space and push the boundaries of scientific discovery, collisions will remain a captivating area of research, revealing the violent beauty and intricate workings of the universe we call home. When we look up into the night sky, it seems like nothing ever changes. The same stars have twinkled down at our ancestors for hundreds of thousands of years. But don't be fooled by appearances. Our universe is never still. Galaxies are hurtling through space, stars are born and die, all around us, worlds are colliding. In fact, collisions are the true architects of the universe. They shaped our world and they'll continue to change everything long after we're gone. Welcome to Future You, where we explore what will happen to the universe and our place in it. Today we're looking at future and our place. Collisions yet to come. Most people know that the Earth revolves around the Sun, and that the Sun, along with our 8 neighboring planets, revolves around a galactic core. But did you know that our galaxy, the Milky Way, is hurtling through space at 820 kilometers per second? And it's on a collision course with another galaxy, Andromeda. The Milky Way and Andromeda are the 2 largest of 30 or so galaxies that make up the local group. The next largest galaxy is Triangulum, which is almost as far from Andromeda as Andromeda is from the Milky Way, and the rest are dwarf galaxies orbiting the big 2. Right now, Andromeda is about 2.5 million light-years away, but in about 4 billion years, it will reach the Milky Way and the 2 galaxies will begin to collide. This will play out over tens of billions of years. After all, each galaxy contains hundreds of billions of stars. Every star pair will need to individually navigate the combined gravitational pull of both galaxies to find its new home in the Milky. To the human mind, this sounds incredibly dramatic. But galaxies are mostly empty space. Stars within each galaxy are so far apart that direct star-and-star collisions will be very rare. Instead, their mutual gravity will stretch and distort both galaxies, eventually blending them into a single elliptical galaxy. Some astronomers use the whirlpool or antenna galaxies as a model for what will happen when the Milky Way and Andromeda collide. The resulting galaxy will retain most of the stars of both galaxies, but the night sky from Earth will look quite different. As Andromeda approaches, it will appear to grow larger and larger, eventually covering the entire northern sky. At some point, its bright core will replace the position of the Big Dipper, and later will obscure the entire region of the sky where the sun sets. It's hard to overstate how dramatically different the view of the night sky will be. If life still exists on Earth, humans will have front-row seats to the spectacle. But not everyone agrees that the collision will be so benign. Some researchers argue that the tidal forces generated by the collision could kick the solar system completely out of the galaxy. Unfortunately, there's no consensus among astronomers about whether or not that will happen. And it's unclear what will happen to the solar system, even if it stays in the galaxy. Simulations suggest that the Sun may be flung into a new orbit farther from the galactic center. Other models predict that the Sun will swing so close to the galactic core that it will feel the effects of another supermassive black hole, the one at the center of Andromeda. These simulations predict that the Sun will then be flung into the outermost regions of the new galaxy, possibly as far away as 130,000 light-years from the galactic center. This distance is more than twice as far away as the Sun is from the center of the Milky Way today. For whatever reason, the solar system is kicked out of the galaxy. Its chances of finding another like it would be extremely low. The closest star systems would be hundreds or even thousands of light-years away. But these potential collisions are only the beginning. Throughout the history of the universe, collisions have been the engines that built galaxies, formed planets, and sparked life. As long as there are objects in space, there will be collisions. Our own galaxy, the Milky Way, was likely assembled in a series of collisions that brought together countless clouds of gas and dust. These collisions also played a major role in the formation of our solar system. Scientists believe that giant impacts between Earth-sized bodies gradually built up the planets over millions of years. Some astronomers even speculate that a planet-sized object struck the young Earth in the past. This collision gave our planet its present size and probably helped set the conditions that allowed life to flourish. In fact, impacts may have played a key role in the origin of life itself. About 380 million years ago, a Mars-sized planet named Theia struck the young Earth. Debris from the impact collected in orbit and eventually coalesced to form the Moon. The impact also supplied Earth with volatile compounds like water, ammonia, and methane, materials that are essential to life as we know it. But impacts didn't stop once life arrived. Comets and asteroids continued to fall to Earth, and some scientists believe that life would not have been able to evolve without these impacts. One theory suggests that the asteroid that killed the dinosaurs actually paved the way for mammals to thrive. Mammals had evolved 66 million years before the impact. but they remained small until the older species went extinct, freeing up resources for mammals to grow larger. Collisions aren't always destructive. Sometimes they can be constructive. In 2017, astronomers witnessed the first collision between two neutron stars. The event was significant because it was the first observation of gravitational waves from a neutron star merger. But it was also important because the collision created an abundance of gold and platinum. These elements are forged inside dead stars and released when they explode as supernova. But this particular explosion was so violent that many more heavy elements than normal were synthesized and thrown into space. Eventually, these elements will become part of another star system and maybe even wind up here on Earth. In fact, scientists believe that the gold in our jewelry was forged in the heart of a neutron star that collided with another neutron star, or a black hole. This means that the gold in your ring was literally born in a collision. There will be plenty of collisions to come. Over the next 100 trillion years, clusters of galaxies will merge into single, giant elliptical galaxies. As many as 100 trillion stars will orbit the supermassive black hole at the center of the Milky Way. But these stars won't all come. From the Milky Way, astronomers expect to see evidence of several dozen globular clusters of stars in orbit around the central black hole. Globular clusters are dense groups of stars that orbit galaxies. Many of them are among the oldest stellar populations in the universe. These globular clusters probably formed in the early days of the universe and were captured by the growing Milky Way as it evolved. Over billions of years, some of these clusters migrated close enough to the center of the galaxy to be torn apart by the gravitational pull of the supermassive black hole. Stars will rain inward, increasing the black hole's mass and fueling the formation of new stars around it. In the far future, as the expansion of the universe slows and reverses, the supermassive black holes at the center of the Milky Way and Andromeda will finally merge. This will create a black hole of about 130 billion solar masses. All of the stars in the galaxy will orbit around this monster. The future will not be completely without collisions. As the universe grows older, white dwarfs, neutron stars, and black holes will continue to collide. These remnants of dead stars are the building blocks of new stellar systems. Sometimes a white dwarf can knock an asteroid off course, setting it on a collision course with the Earth. But for the most part, these collisions will be beneficial. In fact, some astronomers think that planets were largely formed in the aftermath of collisions between asteroids and planetesimals. Eventually, however, the collisions will cease. Over trillions of years, the expansion of the universe will slowly pull the galaxy cluster apart. As the stars age and die, they will burn out one by one, leaving behind a cold, dark, and silent universe. This is what physicists call the heat death of the universe. So while the collision between the Milky Way and Andromeda will dramatically alter the night sky for our descendants, they'll be seeing a pattern that has repeated itself over and over again since the dawn of the universe. From the formation of the first stars to the birth of intelligent life, collisions have been the driving force of evolution. It will continue to shape galaxies, create new elements, and propel the universe forward long after we're gone. For more on the far future, check out our episode on heat death. And for more on near-Earth collisions, check out our episode on asteroid defense. I'm the host. This has been Future You, and our show about the heat death of the universe will air in approximately 9.99999999999 by 10 to the 17th power years. Thanks for watching.